Okay, so today is the first lecture on control theory 1. Um, First, I would like to show the time allocation for the course. The total hour is 32 hours. Uh, so there will be 9 lectures, roughly. Maybe there can be a slight change. And there are 3 tutorials and also 3 practical activity. Okay? And most of practical activity you will use MATLAB and Simulink. So I suggest you to install the trial version. It's fine. You can use it. So the lecture one would be the introduction to control theory one. Okay, so today's content is just two. First, the example of some control systems, where you can find the application of control system. Okay, yeah, for example, motion control in robots, turbine, vehicle, aircraft, and spacecraft. Um, we have power electronics like boost converter, inverter, charge controller, and the next main point I want to show for the introduction is the types of control system. For example, single input, single output, multi-input, multi-output system, discrete versus continuous system, and linear system versus non-linear system. So first, let's see some example of a control system where you can find its application. So application in the motion for robots. Motion control means how you can control the joint of the robot to move to the right angle. Okay. Uh, Let me give a better, more detail on the example. Suppose, yeah, actually, control system is very close to robotics uh, course because robotics is one part and control is another part. Then you can have the knowledge, a complete knowledge to build a robot with uh, motion that you desire. So let me give example of 4 degree of freedom manipulator. So for degree of freedom manipulator, unfortunately this TV screen causes the motion of the mouse is sometimes stuck. But I think it's okay as long as you can see this. So 4 degree of freedom means um, you have 4 angle. Let's say the first motion. Okay, let's say this is the swing at the west. Yeah, you call it the west. Then yeah. Okay, then let's say you want, yeah, let's say you want it to hold 1, 2, 3. You want it to hold something, okay, in a space. Let's say H, Y, Z. So based on the geometry, um, based on the geometry, you know the coordinates. We call an effector, for example, H, Y, Z. Based on this coordinate, you can compute angle called theta zero, and then you can compute this angle theta one, and you can compute this angle theta two, and you can compute this angle theta 3. So theta from 0 to, yeah, I can say given the, oh, one more, given coordinate HE, YE, ZE, and another one is angle with respect to XY plane. Yeah, XY plane, I can, if I draw, another line which is parallel to this one, okay, parallel to this one, yeah, parallel to this one, then this angle is called phi E orientation. Yeah, this example is very close to robotics course. Um, so from theta 0 to theta 3, you mean 4 angle. So given 4 known variable, and you must create equation to solve for these 4 variable. So it's fine, you can find it, you can find them. Then with the knowledge of this theta, you apply the control system to control all the motor to rotate to this angle. So which means you will finally have your end effector at the position you want it to. See, you got the concept. So this called this 4 angle. Okay, yeah, is a function, a function of H E Y E Z E and phi E. You compute from them, and then you call this one as desired angle, desired angle. Okay, which means you want your motor to rotate to these respective angles. So of course you will assume the end effector is the position H E Y E and Z, and the orientation phi E. Okay, that's the idea. So control theory is applied to how you control the motor or the system in such a way that you can achieve the desired angle. Okay. Another application is, for example, the Segway. In this application, your objective control is first you want stability. You must keep it straight like that in such a way that your posture is comfortable with it, and then you want to control the speed when the user just lower the bodies a little bit or just push the body to the front a little bit and it's increase the speed, for example. So you need to control two objectives. First, make it stable, and you can control the speed. Okay. So this one is to output. Okay. Yeah, to output. And another application of for in control is also in robotics. So in here, you want to control a three-wheel robot. So you need to control the wheel or the three wheel in the right way so that you can achieve whether it move in the direction of H. Let's say I have three wheel. Okay, three wheel. Yeah, it should be 120 degree. Yeah, and then you choose the direction. Let's say you choose this is X axis and you choose this is Y axis. So from kinematics, from kinematic, you choose, you desire, you want the velocity in, for example, in this way. You want the robot to move in this way with a certain value vx and certain value vy, and then certain vy. Then you can compute um, the velocity of each wheel. So velocity of each wheel must rotate in a certain way such that the robot can move in this direction, right? And then you apply the control theory into the motor, that how you can design controller that you can make those motor rotate at the desired velocity. Okay, this is how you apply control system. Um, yeah, this is very similar. It's the same thing. This one is just to um, why cannot oh, when this one, oh, I see, when it detect the pen, so in this robot, we we input the equation of a circle in a circle like this as a desired trajectory, and then we compute based on kinematics, and then implement the control theory to make the robot move along the trajectory that we input. So equation of circle, you can write it, right, in terms of time. You can easily, yeah, so it's one round from there to there here. Yeah, so it means you input the desired equation like h of vh, the velocity and the direction h, in function of time. Let's call uh, a cosine omega t, and you have vy as a should be the radius. No, if is this not h, yeah, if this one should be h in this case. If I use this as h, this one should be the radius itself. Is y sine omega t. So you just give the command to the robot that you must go along this trajectory. And then we have a control theory with architecture of a control system and design controller, and then compute the voltage to each motor to make the robot move through the trajectory. Okay? Yeah, well, similarly in this application, from kinematics, we compute if you want the trajectory of the if you want the trajectory of each leg here like this in a certain velocity, and then we compute what is the velocity of each joint, and then we control each motor to have such velocity. Okay. Um, all right. I think I can give another example. So not yet. Let's go to the second point. Yeah, I will give more example when we uh, discuss about multi-input, multi-output system. But okay, so the main second point for today is the types of control systems. The first one is called single input, single output. What does it mean? Single input, it means what you can command, what you can provide the power to the system in terms of one parameter only, one variable. The Yeah, because a system, in order to have a system evolve, you need to provide in power, right? And then it may convert to another form of power. For example, you input as electrical and power, and then it move. It means it's generate mechanical power. But anyway, for that the input power, what you can play around is just only one parameter. For example, it's just voltage or just current. You can only play around with the voltage. You can increase voltage. You can, but you don't know current. You don't care about how the system draw the current. You don't care. So you only play around with voltage. Then it means just one single input. And for the output, uh, if you are interested, you are interested in observing velocity, you want to measure velocity, then it means you have only one. You want only one output. Okay? But if you want output as velocity and also torque, then that will be two output. Okay? So, but for the system, single input, single output means the system, for example, a DC motor, and I represent it by a block diagram. In our future lectures, we will talk a lot about block diagram. So let's say the input is voltage, and the output is angular velocity. Velocity. Then you have only single input and single output. Another system, another example is like boost converter. Yeah, in the previous semester, you already study power electronics. So, boost converter. Let's say you want to the input that you can play around is duty cycle in this case. Duty cycle. Okay. Yeah, of course, your system you have input voltage source, and then the output voltage is what you want to observe, or you desire to have a certain level of voltage, for example. And what you can play around is to program the duty cycle. You can change the duty cycle so that the output voltage can change. Okay. Yeah, this is also a single input, single output. Um, a pendulum of single pendulum, also single input, single output. Oh, another example, car suspension. Car suspension, just single. Imagine that you only study one suspension. So the lump model, lump mean simplified model, like this one, mass, and then you have a spring, and then you have a damper, and you have a road, profile of the road, like this. So when you have velocity in this direction, this is h, and this is y direction. If you have a profile of the road, so you move with a certain velocity like this, and the road is not flat. Yeah, assuming it's not flat, then you have profile velocity in this direction as well. And the velocity of this direction becomes the input to the system. And your output, if you want to observe, you observe the height to a certain level of the ground. Let's say initially you start at a zero around this. So the height of motion of the car is the output. So the input is velocity due to the low profile with a certain velocity in the horizontal direction. Okay. If you go this way fast and your road profile is like this, your road profile is straight. But if you move horizontally too fast, the velocity profile in this direction also fast, right? So this becomes the input to the system. Okay. So with this velocity, then the motion, the height of this one will move to a certain type. Okay. And that is the output of the system. Okay. Net multi-input, multi-output system. Just like I showed you earlier, the 4 degree of freedom robot manipulator. So actually you have, yeah, if you consider uh, yeah, you consider the output as the position x, y, z, and phi n effector. Sorry, n effector. The input is the voltage. Uh, you have 4 inputs. Those are the voltage of each motor, voltage that is applied to each motor. So you have multiple input and you have multiple output, X, Y, Z, and phi. Okay? Not single anymore. But if you only narrow down to see only one motor, you don't care the structure, the mechanism, you don't care the dynamic of the system, you only care, I will try to control the motor in the way that I put I want to control velocity or I want to control the position, and you don't care the dynamic of the robot, then you can simplify it to study only one motor, then it's just SISO, single input, single output. But you want to study all the dynamic of the structure of the robot. So from the motor model with the voltage input and then the output is the position and velocity of an effector, then you have multiple input, multiple output. Okay. How about a quadcopter? Yeah, for a quadcopter like drone, you have 4 propeller. Each propeller you have one motor. Okay, one motor here. Okay, one, two, three, 4. You have 4 motor. So the propeller produce thrust force in this direction. Okay. Yeah, and also produce torque in each propeller. Sorry. So the equation, the dynamic equation for this drone is, okay, motion in space, right? In the 3D space. So object in the space that you have 3 dimension. So it has position. Okay. Equation of translation, you have translation motion. Translation. And you have rotation. So the translation with position and velocity. Then you have six state. Okay, this is 6 state. And for rotation, you have angular velocity 3, and then you have just sometimes you want to use Euler angle. Yeah, you don't know what it is now. I just want to tell you that for rotation you can describe it using 6 parameters as well. If you want to describe only position, then you need only 3 parameters like Euler angle. But if you want to describe the motion including the velocity, I mean position and velocity, then you need 6 parameters. Angular velocity at the 3 axes, and also the Euler angles. So plus another 3, you have 6 for rotation as well. Then the total is 12. Yeah. So for this 12, if you want to control angular velocity, like oh no, you want to control the trajectory of a drone. So it means each position it has one portion of the central mass, and then it has orientation. You mean rotation. So you want 6 output, for example. You want 6 output. Okay. You want 6 output, and for the input that you can have for the system only 4. How can I count it 4? It is come from for the Newton equation. For translation, you need force in 3 direction. Force in 3 direction, right? Fh, Fy, and Fz. But our thrust on only the same direction for all propeller. See, all same direction. You cannot have this direction. You cannot have that direction. Which means you cannot have if I write it on the body frame of the drone, you only have one direction, which is on the z-axis. So the input you reduce to only one is thrust, which is t, and the direction is z-axis. Z-axis on the body frame. Okay, and for the moment, uh, if the thrust of each propeller produce different value. For example, if this side is stronger, and then you produce torque in this direction, right? But if the force on this side is stronger this side, and then you produce torque in this direction, okay? Like this, or like this, or like this, or like this. Okay, many ways for the torque. So it means you can generate torque in all the 3 directions. So input only T on the Z prime, Z with the body frame. This comes from thrust. Okay, thrust. And then torque. Yeah, I use here is sorry. Maybe it's better to use F because yeah, just use this F. Okay, and then I use this one as top T H T Y and T Z. Okay, prime with respect to body frame as well. So this is input to the drone system, and the output is position x y z, and the orientation, the rotation, the Euler angle. Okay, Euler angles. 3 plus 3 then 6. So this is a type of multi-input and multi-output, and sometimes the number of input and output are not the same. Then controller design become more difficult. Okay, the next point is the comparison between discrete system and continuous system. So discrete system, you describe the dynamic equation by index k. So it has the form of like hk plus 1 equal to f of hk and input uk. Um, so why discrete system exists? Yeah, actually, when you apply digital control, you program to compute a certain voltage or compute a certain amount of input and inject to the system. You need a certain amount of time to compute, right? Even though your computer is very very fast, but at least it needs some time to compute. So um, so the profile of the input volt, the input, let's say, okay, this is T, and this is input U. It can be voltage or can be current, okay, or can be thrust. So because you need certain amount of time to compute something, to compute the input, the right input. So let's say during this period is computational time. Computational time. So I call this one TS, this one 2 TS, 3 TS, 4 TS. Let's choose example. TS equal to 0.001. Yeah, just example second. So you give the time to the processor, to the digital computer to compute. Yeah, you give the 1 millisecond. Uh, you give 1 millisecond to the processor to compute the to compute the value of input. Let's say at first sampling time you can compute at this value, and the next sampling time you compute it at this value. The next sampling time you compute it at this value, and the next sampling time maybe drop to here. So this is a form of discrete. Yes. So the controller computed that okay, the input voltage should be this, and then it command to the driver, and the driver set the voltage to control your device. For example, a DC motor. You got that? And it so after it does give the value voltage to set it, and then it compute again that what is the net value of the input, okay, in the next sampling time. So it do this like that. That's why in application like this, it's always discrete, not continuous. The system you derive from the physics always continuous. But when you apply digital control, you are not using analog control. Your controller is digital. So the digital you need a certain time of computation. At least if you have very very fast processor, you may need 0.1 millisecond or 0.01 millisecond, for example. Yeah? So always discrete. And continuous system, yeah, you have it from physics. You derive equation from physics. You have a circuit, for example. Uh, you have circuit like RC circuit, the most simple one. You have RC circuit. So the input is U, and then the output is the voltage of the VC. You derive the equation. It has the form of differential equation. VC dot equal to no, VC dot plus, I don't remember it well, or plus 1 over RC, maybe 1 over RC VC, and equal to U of 1 over RCU, RC times U. Yeah, not, maybe not correct, just the form is like this. It first order differential equation and it's continuous. If you solve it analytically, if you solve it using analytical method, you get a continuous solution, right? You get continuous solution. Yeah, I admit that my writing sometimes is not correct. I mean, my English writing is not always correct. So, yeah, just ignore it. Just focus on the concept and the technical part. Okay. Um, the equation, I think, yeah, if u is constant or step, if u is constant or step, the input output voltage VC is um, u1 minus e to the t minus t over all c, like this time, yeah, t minus all c. I write here the input would be VC equal to u 1 minus e to the minus t over rc. Okay, so this is continuous, which means you can compute VC at any instant of time you like. Just for t like equal to this, t equal to that, you can compute VC at that instant of time t. But for discrete, once you choose sampling time Ts is 1 millisecond here, and then 2 millisecond here, 3 millisecond here, 4 millisecond here, and let's say you never get the value of u at I mean the exact value of u at the time 2.5 millisecond. Like you cannot, right? You cannot get the exact value of u in between the sampling time like that. Okay. Yeah, this is discrete. So analytical solution can provide you the solution at a function of time. It means its continuous form. But numerical method, numerical solution will only provide you the solution at certain sampling time. Okay? And that is uh, always used for the application in the digital control when you program to a microcontroller. Yes, so you must be clear at this point. So when yeah, you want to apply to the real control system like DC motor or to the robot, then you can clearly see that the way you program to compute the controller is to use the discrete form. Okay. Now, come to the last part of the introduction. Linear system versus nonlinear system. So after I finish this part, we will have a break. Okay. Oh, I can give you 10 minutes. Oh no, 50 minutes. Break. Okay. So let finish this first. Uh, so for linear system, to be precise, that we have analytical method to solve equation and to do the analysis. It's called linear time invariant system. Actually, linear time invariant invariant system. Okay. Um, so the property of linear system is that you look at the differential equation. If all the coefficient of the differential term are constant, then you say the system is linear. Okay. All constant of all coefficient of differential term are constant. Okay. Yeah, for example, I just give you a RC circuit, uh, VC dot plus 1 over RC VC equal to U equal to U. You see, so the coefficient here is 1 constant, 1 over RC constant if R and C are constant. See? 1 over C here as well, 1 over RC here, 1 over RC times U. This RC circuit. How about RC circuit? RC circuit? No. U here, C, L here, R here. Okay. Yeah, also you derive this, you get the linear system as well, okay? Linear equation as well. Um, I give another example. Mass spring and damper. Yeah. Another example is mass spring and damper. Mass spring and damper. You have spring and you have damper and you have mass here. This is spring constant and viscous coefficient. Okay, so let's say you have input as a force to the system, and the equation would be h bar dot h bar dot plus c h dot plus k h equal to u. So you can see that coefficient or coefficient are constant. Okay, then this is a linear system. How about nonlinear system? I can give example. Even a simple pendulum, yeah, even a simple pendulum system like this, yeah, with Mach m, and you want to derive the equation to describe the angle of theta. The equation um, look like this: theta double dot plus uh, um, g over l sine theta. So, no, the over l. I don't remember this well, but well, just equal to g. Yeah, I don't remember it, but we can easily derive it. What I want you to notice is that you have a term here, you have a term here, a sine theta. It's not theta like this. If you have theta and if the coefficient is constant, I mean are constant, then you have linear system. But here you have a function of theta which is not a linear function. Okay? Then the system is not linear. How about the quad-quarter system that I just gave earlier? Of course, this is not linear. A very complicated equation of the rotation. Okay, the equation, rotation equation and kinematic equation for the in the motion in the 3D space is highly nonlinear. Okay, this is also nonlinear. So if you observe that the how you can have a linear system, actually this system you can see that the inductor is made by engineer, the capacitor is also made by engineer, resistor also made by engineer. So the engineer try to make things simple, try to simplify things. So they try to make inductor that have constant inductance. They make capacitor that have constant capacitance. They make resistor that have constant resistance. Then you have a circuit that can be described by a linear equation. And you see the mass spring damper also. Okay? Damper is also we can make it in a certain way using fluid inside a cylinder and have a small pipe allow the fluid to move, and also the spring you make the nice shape of the spring with a constant profile of spring. Let's say you have a extension spring, then you can have linear system. But if you look at the nature itself, even the pendulum, you can see many places in the nature. Let's say a tree fall down, or a branch of tree fall in a whale's pendulum. Just example. Um, then you can say that the motion of the pendulum is not linear, and even the motion of a planet around the sun the motion of the moon around the planet described by Newton equation or Einstein equation are all nonlinear. Okay, nonlinear. But fortunately, many systems uh, we we can control it by look at the linear version of the nonlinear system. I mean, we can derive equation for a system which is nonlinear, but then we do the linearization and we can look at the linearized version. We can design controller to the linearized version, and those controller can be applied to the nonlinear system. Many systems, even for aircraft, the commercial aircraft. The equation is a motion in 3D. It has 12 equations, 6 for translation, 6 for rotation, very highly nonlinear, but you can do the linearization and you can look at the relationship of a single input to single output directly. I mean, simplify, discipline the system. For example, the motion of the rudder of the wing will cause to the rotation of the aircraft, and you just locally look at that. You can design a simple linear controller and can apply it. And many systems can be done that way. But of course, many other system you want the degree of robustness, degree of performance higher, then you must design nonlinear controller and apply to it. Okay. Yeah. Like I mentioned, for the commercial aircraft, the motion is always the rotation not too much, never up to 90 degrees for sure, right? Rotation on the roll, not up to 90 degree rotation of the pitch, not up to 90 degree. Okay, the yaw is fine. Okay, it can rotate a long time and can mini round is fine, but the roll and the pitch, so that we can just linearize it and control it with their range. The range is fine. But if you apply the same controller to the fighter jet, they can rotate many degrees or the pitch or the roll, that will be a disaster. Okay? You cannot apply the controller that you design for the linearized version and apply it to the nonlinear system that have very complicated motion. That's not work. That's not working. Okay, so it's very important to uh, understand the limitation of simplified system or some controller design for a simplified system. Okay. Yeah. Final. Yeah. My final word for this 1 hour lecture is the direction to the future on the control system that you need to look at first for the single input, single output, and yeah, okay, linear. This one I O. If I make table like this, nonlinear. Okay. Uh, so for the control theory one, you will look at here only. Okay. Maybe at the end of the lecture, we look at a little bit here, maybe just a little bit. Okay. And yeah, we may look at some nonlinear system, and then we do do the linearization to go here. Okay, linearize, yeah, to go linearization. Okay, so mostly we will talk only here. And for the control theory two, yeah, you will, in the next year, yeah, next semester, if you choose robotics and automation uh, concentration, then yeah, you will study here and here as well. Okay, yeah. All right, I finished now, and you have a 15 minutes break. After then, you come back and we can have a question and discussion.